So heat evolved at constant pressure. We talked about constant volume. When a chemical reaction occurs in a container that's open to the environment, the pressure inside the container will be equal to the pressure outside, which is atmospheric pressure. And so this is a very easy type of situation to have. So when we do have it open to the atmosphere, constant pressure, the volume of the things involved in the reaction can change. And so we can have energy evolving as both heat and work. So that's more complicated. But oftentimes we're only interested in the heat exchange. The work that's done isn't useful, and we're just not that interested in it. So we have to introduce another term referring to heat, and that word is enthalpy. It's a funny word, enthalpy, and it has the abbreviation H, capital H. I have no explanation for that. It is the sum of the internal energy and the product of its pressure and volume. And this is how it was defined. So the enthalpy equals the internal energy of the system plus the pressure of the system times its volume, just because they said it is. So enthalpy is a state function. The internal energy of the system is a state function. The pressure, the volume are state functions. State functions do not depend on how you get from one point to another, just the beginning and the ending. So if we look at the change in enthalpy, the change in enthalpy ends up being the heat that's evolved at constant pressure. And so that's how this works. We just said that H equals E plus PV. So the change in H will equal the change in E plus P times the change in V. It's not the change in pressure, because we said the pressure's going to be constant. It's not going to change. Well, we know that delta E equals Q plus W. Now we're going to put a subscript P on this Q. This is the heat, that's the work. This is heat at constant pressure. So we're substituting in Q plus W for delta H. And then here we have this P delta V term, which should look a little bit familiar, because earlier we defined work, pressure volume work. Work equals negative P delta V. Right, we said that earlier. So then P delta V would equal negative W. So for this P delta V term, we substitute in negative W. Now we have Q plus W minus W. The W's magically disappear, and the change in enthalpy is equal to the heat evolved at constant pressure. So we've got delta H and we've got delta E. And they are similar in concept. They're involving a change in energy. And oftentimes the value of them is similar, but they do have intrinsic differences. Delta E is a measure of all the energy exchanged with the surroundings, so heat and work. Delta H is a measure of only the heat exchanged under conditions of constant pressure. Most of the time, the difference between them doesn't matter. The difference is biggest if you have a reaction that either uses large quantities of gas or produces large quantities of gas, such that the change in volume is really large. Then the difference can be significant, but most of the time that's not the case. Signs for delta H and delta E are going to follow the same conventions. Heat or energy going out is negative for the system, coming in is positive. So if delta H is positive, we're absorbing heat. This is called an endothermic reaction because endo into thermic heat, so heat coming in. If delta H is negative, that means that heat's being released from the system, and that's an exothermic, exo like exit, going out, so energy going out. Any questions? You do need to know these terms, exo and endothermic, and how that corresponds to the signs of delta H. We talked about hand warmers, chemical hand warmers, iron filings inside of them mixed with oxygen from the air, And that is an exothermic reaction. It gives off heat. This is why these little packets warm your hands, right? Because they give off heat. You can also have chemical cold packs. Most of these contain ammonium nitrate. And as that dissolves in water, it's an endothermic process. It's absorbing energy from the surroundings. And so your hands, when you hold this, or your elbow or whatever needs icing, gets cold because the cold pack, that chemical reaction is sucking energy out of the surroundings. So we should be able to identify processes as endothermic or exothermic. We should be able to tell what the sign for these things is, the sign of delta H. These are not always immediately obvious. So the best strategy really is to be able to think it through. So let's think about this. An ice cube melting is that process absorbing energy or releasing energy. Well, we could think about what would we do to make the ice cube melt faster? Would we heat it up? Yeah. So if we put it on the stove and turn the burner on, the ice cube will melt faster because we're putting more heat in. So that tells me this is an endothermic process. Energy is going into the ice cube to melt it. So this is endothermic. If it's endothermic, then what is the sign on delta H? It must be positive because energy is coming into the system. If I get a deposit into my bank account and I go look at the statement, it's a positive number, right? And I feel good about money coming in. So delta H is greater than 0. Positive. Any questions about that? Nail polish remover quickly evaporating after it's accidentally spilled on the skin. Now I know you guys remove nail polish all the time, right? No. So some of you may not have ever spilled nail polish remover. Girls, what does it feel like? It's cold. It's a lot like alcohol, like, get an immunization and they wipe your skin with an alcohol wipe. It's cold. So that's the little piece of information that's very helpful in understanding this. The other word that you could use here, evaporating, if you've never experienced this, you don't know that it feels cold, you could figure this out from the word evaporating. Evaporating is going from a liquid state to a gas state, right? That's evaporation. How do you make something evaporate faster? You add heat to it. The nail polish remover, which is acetone, evaporating on your skin is absorbing heat from your skin, and that's why it feels cold. So is this exothermic or endothermic? It's endothermic because heat is going into the acetone to make it, the nail polish remover, to make it evaporate. Any questions? So endothermic, again, delta H is going to be positive. Gasoline burning within the cylinder of an automobile engine. Exothermic. So burning. Burning is always an exothermic reaction. And we think about, well, what happens when I burn a piece of wood? What happens when I light my Bic lighter and burn the butane? What happens when I turn on the gas burner or a Bunsen burner, right? It gets hot. So energy is leaving the system, it's coming into the surroundings where we are, and we feel the heat coming off. So this is exothermic, and delta H will be what? Negative. Exothermic, delta H is less than 0, it's negative. Any questions? There will be at least one question like that on your exam. And it might not be something that's obvious. The ice cube melting one isn't too difficult. What about freezing water? Is that exothermic or endothermic? It's exothermic. So we tend to think of exothermic as something that feels hot, right? But when you freeze water, that doesn't feel hot. But freezing is the opposite of melting. So if melting is endothermic, freezing must be exothermic. The way your freezer works is it's sucking heat out of the inside to make it colder. And as something freezes, it releases heat. So some of these can be tricky. Any questions? Well, let's look at a molecular view of what's going on in these exothermic reactions. Exothermic gives off thermal energy, causes the temperature of the surroundings to rise. So where is that energy coming from? That extra thermal energy comes from the stored chemical potential energy. We're converting some of that potential energy stored in the reactants into kinetic energy in the form of heat. And that is what's released into the surroundings. In the course of the reaction, in the course of any reaction, you have bonds being broken and new bonds being formed. And what determines whether this is exothermic or endothermic is the relative energies of those bonds. So here in an exothermic reaction, the products have less chemical energy than the reactants do, because that initial stored chemical potential energy, some of it was released, and so now the products have less energy. The difference is that energy that's released as heat. Endothermic is the opposite. The temperature of the surroundings drops because the reaction is absorbing heat energy from the surroundings. Again, we have bonds being broken, new bonds being made. But now the products are going to have more chemical energy than the reactants did. And they got that energy from the surroundings. Some of the thermal energy of the surroundings gets converted into potential energy stored in the products. So any questions about that? So we talked just a minute ago about change in enthalpy. So if we look at the enthalpy change for a chemical reaction, we put RXN, which is our abbreviation for reaction, as a subscript after delta H. So this is the enthalpy of reaction or the heat of reaction. This is an extensive property, not an intensive property. It depends on the amount of stuff that reacts. If you burn a teaspoonful of gasoline, or if you burn a tanker full of gasoline, is the amount of energy released different? Oh yeah. The tanker burning is going to give off a tremendous amount of energy. So the amount of energy released depends on the amount of stuff. It's an extensive property. So by convention, what we do is we express delta H reaction, the heat of reaction, for the number of moles in the chemical reaction that we write next to it. So here's propane combining with oxygen to form carbon dioxide and water. This is the balanced chemical equation for the combustion of propane. And we show the heat of reaction here as minus 2044 kilojoules. So the negative sign tells us this is an exothermic reaction. It's releasing this much energy for 1 mole of this. For 5 moles of oxygen, if we produce 3 moles of carbon dioxide, this is the amount of energy released, or 4 moles of water. So we can make conversion factors between moles of substance and amount of energy. So 1 mole of propane would give this much energy, 5 moles of oxygen. So this allows us to convert between energy and moles of substance in one step using the balanced chemical equation. Let's do an example. Ammonia reacts with oxygen according to this equation. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. So we have 155 grams of ammonia, 155 grams. And we're not asked about how much product is made. We're asked about how much energy is released. So there's the energy term, so I'm going to put my question mark over there. This is stoichiometry, but with energy. So regular stoichiometry is grams to moles to grams. That's always a good starting point, and then we just make variations. Well, what are we given? We're given a mass. Well, that's okay. So we've got grams to moles, but we're trying to get to kilojoules. So we definitely don't need this thing at the end. We don't need to go to grams. We're trying to go to kilojoules. The beauty of this is, though, this amount of energy relates to any mole or molar amount in this equation. So I don't have to go from moles of ammonia to moles of NO and then to kilojoules. I can go from moles of ammonia directly to kilojoules. So I don't need this second mole step either, and I can just go grams to moles to kilograms. So I'm going to have grams of ammonia to moles of ammonia, and then directly to kilojoules. Because what this is telling me here is that I get minus 906 kilojoules for how many moles of ammonia? 1. The coefficient over here, wait, no, not 1. What's the coefficient? 4. So 4 moles of ammonia will give this much energy. So I've got minus 906 kilojoules per 4 moles of ammonia. That's the conversion factor I need to go from moles to kilojoules. So grams of ammonia to moles of ammonia directly to kilojoules. And then I put my units in so they work out. And grams of ammonia. So this is the thing I just figured out. This is the delta H, the heat of reaction, and it is negative. And that's for 4 moles of ammonia. And then I need the molar mass, which you can calculate. Happen to have that stuck in my head. So 155 divided by 17.034 times negative 906 divided by 4. So the calculator shows me negative 2061.025 and some other digits. And the unit that's left that isn't crossed off is kilojoules. How many sig figs? 3. I've got 155 kilojoules here, and I've got, grams. 906 here. That's exact. That's got more than 3. So I need 3 sig figs. So be careful. 2061 is not even close to 206. So when I round off the 6, I have to replace the digit that I'm getting rid of with a 0 so that I don't change the value. So 2060 kilojoules, or scientific notation is always good here, minus 2.06 times 10 to the third kilojoules. Any questions? The sign on delta H can be a little confusing sometimes. Now, in this question, it says calculate the heat associated. Does associated imply a direction of going out or going in? It does not imply a direction. When the direction is not indicated with the words, then I do need this negative sign down here. If the question said calculate the heat in kilojoules released by the complete reaction of 155 grams, then I would not put the sign on it. I would say 2060 kilojoules are released. It's like when we purchase things. Oh, I bought this screen protector for $8 on Amazon, right? I don't say I bought it for negative $8. If I bought it, that means I spent the $8, right? So we don't need the negative. So that could trip you up a little bit on Mastering Chemistry. I won't try to trick you with that on an exam, but just be aware.